So good morning, everybody.
Good morning.
So the irony is that the Balo clan got sick for Thanksgiving. On Saturday, I couldn't even get up. I probably shouldn't be here today. I should probably be wearing a mask. But we have 4 class sessions left, not counting labs, right? We've got this week and next week. And I simply cannot afford to leave you in the lurch. Right? 2 chapters to go. So, I apologize today if lecturing in my sweats is not something you're supposed to do. I don't care. And I also apologize. This is not going to be high energy. Okay? This is going to be survival. We're going to get through this, right? And we'll see where we are on the other side. The quiz sheets, I don't need them today, right? I'm throwing up these instructions right now for you to kind of collect them, bring them next time. The sooner you get them to me, the sooner I can put them into Canvas, right? And the sooner you can have a more accurate grid in Canvas, right? So instructions are going on the screen. I don't want to belabor it. The important part is your name and the grand total on the front. Right? Go through all of your sheets, add up all the points. Not what it's out of. I've got that record. And so just the total points you've got, write it on the front. I have to make some adjustments because I didn't hand out enough quiz questions. I kind of slowed down there for a little bit, and that was my bad. So it's not going to be out of 50. It's probably going to be more like out of 30 or so. So, but whatever you've got, right? Whatever your total is, just write it there. And I will go through, check them to see if it's justified, and then enter a score into Canvas. Also, if you could, please put the lab that you're in, right? Whether it's the 8 a.m. or 11 a.m., section 1 or section 2. That would be good. All right. Somebody asked me about final exams, so I just looked it up. Your final's on Monday, 8 o'clock in the morning, in this room during finals week. Right? So don't go to the lab. There is no lab that week. We have to obey the lecture schedule. So come to this room on Monday morning at 8 o'clock. And then you don't have class for the rest. You don't have physics for the rest of the week, right? So that's coming down the pipe. Get your exams back this Thursday. What have I forgotten to tell you for the last end of the end of days? No, the end of the semester. I'm sure I'll remember something here as time goes on. All right, want to finish up chapter 15, and then move on to 16 and try to get a good healthy chunk of 16 out of the way so that you can dig into the homework and be done there. The thing we didn't finish up in chapter 15 is this concept and idea of what happens when you add friction to a harmonic system. So this is no longer simple harmonic motion. We call this damped harmonic motion, where dampening is a term that refers to a force that's acting against the oscillation. So I think the best way to imagine this conceptually is instead of a mass like bouncing back and forth on a spring, or maybe even up and down on a spring, imagine that mass is in like honey or oil, some thick fluid, right? You can kind of imagine if we pulled it down and let it go in that medium, it would kind of slowly, like it might bounce up and down once or twice and then just come to a stop as friction robs it of all of its energy. So that's a damped oscillator. I put a picture of a real damped oscillator up here on the screen. Does anybody know what that is? It's a suspension strut along with the shock absorber and the spring. Why does your car have springs in the suspension? What does your car want to do when it hits a bump? It wants to go up and down, right? Okay. And the spring is there, okay, to provide an oscillation. It's much better. Anybody that has ever been in a vehicle with no suspension, okay, knows how rough that is and how easy it is to lose your kidneys. the suspension system, even since the age of stagecoaches and carts, were there to provide impact reduction from bumps in the road. And they found out that by bouncing the vehicle up and down, you could relieve some of that initial impact. Now, the problem is that if you don't have any dampening, what is your vehicle going to do? It's just going to keep bouncing up and down, right? Okay, and that's bad too. So you use the spring to absorb energy, in a sense, to provide an oscillation, but inside the spring, you can see it down inside there, is a strut with a shock absorber in it. And the idea of a shock absorber is to take that bouncing motion that the spring is going to give you and rob that spring of the energy in a safe and comfortable way. So there are 3 kind of categories. We're just doing this conceptually, okay? But there are 3 situations that damped oscillations can be summarized with. And those 3 are critically damped, overdamped, and underdamped. Let's do underdamped first. So the underdamped case is where you get a wiggle, where there's friction in the system, but it's not enough to prevent the harmonic motion from happening. The amplitude's dying, right? That's what the friction does. That's what the dampening does. But there's still wiggle there. You know, there's still frequency and things like that. And again, we call this the underdamped case. And then there is overdamped. In the overdamped case, what we have is kind of this long sort of decay towards equilibrium. There's really no harmonic motion that we would recognize. There is so much friction in the system that the oscillator just kind of, you let it go, just kind of goes, and then just stops at its equilibrium position. And the amount of time it takes to get back to the equilibrium position is utterly dependent on that friction, that dampening that's in there. So we call that the overdamped case. Okay? And then the critically damped case, critical dampening sometimes it involves a little bit of a kind of oscillatory motion to it. But in any case, it's a quick return to the equilibrium condition. And this does vary slightly depending on kind of who you're talking to and what the application is. Because sometimes, don't draw this one, a critically damped is just a return directly to the equilibrium. Okay? But in the critically damped case, it's like you've kind of nailed the dampening just perfectly to get an oscillation, but it very quickly returns back to its equilibrium condition. Where would we apply this? Let's talk about designing suspension in cars and comfort and safety. So if you've ever, I'm not sure how to put this in a politically correct way.
Go for it.
Just I should just say it? Yes. Yeah, we're friends here? No, I should be careful. This is on YouTube. There is a segment of our population that has had more life experience, let's say. Their hair is changing colors, and they have no control over it. They tend to be wiser. What did you say?
Old people.
Okay, you said it, not me. Right? Okay. And there was a particular car that was marketed to this age group. What was it called?
Town car? Lincoln.
Who made it?
Lincoln.
No. It's a company that doesn't exist anymore, so I'm not surprised you don't know. Oldsmobile. Oldsmobile. And it was named like, okay, so the Lincoln Town Car, the Oldsmobile. What did these things drive like? Have you ever been in one of these? An old person's car?
I've seen them around a lot.
They're like Lambos, right? They're like, first of all, steering wheels are huge. Just like a boat. Okay? Yeah, Buick, always in good, right? And the car, like, floated places. Like, you'd be driving along and you hit a bump and it'd be like, right? Like nothing happened. The suspensions were soft. You did not corner in this vehicle. Making turns was hazardous to life and limb because the front end of the car and the back end of the car were separated by what seemed like 3 continents and 2 years. Like, you would put a turn in, and the front end of the car would go, okay, I'm turning. The back end of the car would say, wait, we're turning? What? Right? And before you knew it, the car was, you would go around and turn, right? Okay? Kind of had to plan ahead 3 or 4 weeks before you did turn. The suspension in those cars was not tuned for performance. Okay? It was tuned for comfort. So which of the 3 cases do you think that might be? Under, over, or critically damped? Where you've got a car that drives along, right? It hits a bump and goes boom. What is that? That's over damped by a lot. Okay? That's like, hey Martha, did we hit a bump? I don't know if it is. Right? It was just like, you couldn't tell that anything was happening. Okay? And then on the other side of that spectrum, you have trucks. Okay? 1-ton pickup truck, let's say. Okay? With no load in the truck. Now, a 1-ton pickup truck is designed to carry what? A ton of stuff. Right? That's sort of the limit, right? And it's actually tuned. The suspension is tuned for approximately half of that load, a little bit more than that load. The suspension has to do a lot of things over a very wide load parameter, over 2,000 pounds of cargo. So what they'll do there is that when the truck is empty, it'll actually be in a critically damped case. Anybody that's ever been in an empty truck knows that suspension is just awful, right? The ride is just sharp, right? You feel every bump in the road. And the vehicle seems to handle better and smooth out when you're actually hauling something. Like, heaven forbid anybody has a truck that actually moves stuff. I've seen a bunch of trucks here in Fresno with a lot of trucks, but not a lot of stuff in them, right? Okay? And then you've got sports cars and other things where the suspension is tuned very, very strongly. From a point of view of a ride, right, in passenger comfort, it would seem like the overdamped case would be like perfect, right? But let's talk about safety. What is the wheel doing in the overdamped case? You hit a bump, the wheel goes down and then starts to come back up, and as the wheel is rising up, what's happening to the normal force between the ground and the wheel? It's decreasing, right? Because the wheel's on its way up, and so the amount of down force from the wheel on the ground is lessening. The normal force is getting smaller and smaller, right? Wheel's not pushing as hard on the ground, so the ground doesn't push as hard back. And what happens to friction when the normal force reduces? It goes down as well. Remember how fun it is? So it's actually kind of dangerous to have an overdamped suspension. And so what the brilliant engineers at Oldsmobile and other car manufacturers did in order to overcome that is they started playing around with the speeds that the wheels would turn depending on what the suspension was doing. And mechanically, okay, they were able to do this long before the computers. Now computers just control everything. But mechanically, they were able to alter the rotation rates of the wheels independently. The faster you spun a wheel, the more grip the wheel would have on the road. And so as a tire began to come up, the wheel would spin a little bit faster to try and maintain that friction on the road. It wasn't perfect. Computers do a better job now, especially with adjusting the suspension on the fly. But it was a way to get around the safety issue. For pure safety, which is the best one here? Which is the one that maintains the tire on the road at all times? Critically damped. Critically gets it back to that equilibrium position as fast as possible. Takes the wiggles out. It also makes the ride pretty stiff. All right, so that's dampening in a nutshell. I didn't show you any of the math because the math is awful. And I just want you to know about it conceptually. The other conceptual bit I want you to understand when it comes to oscillations is what happens when we do sort of the opposite of dampening. What would the opposite of dampening look like? This is called a forced oscillation. This is where we're going to take a harmonic system and with a set frequency and period, okay? And we are going to force it. We're going to add energy or apply a force at exactly the right moment. You don't have to, but generally all of our examples are going to be adding a force at exactly the right moment. Can you think of an oscillating system that is an everyday experience, or mostly everyday experience, especially for people under the age of 12, where you are purposefully adding energy at exactly the right time? Say it loud.
Swing.
Right? Go on to swings. Okay? You have an oscillating system there, right? Got a pendulum, okay? It's got a frequency, it's got a period, it's got all that stuff, okay? And when do you do that pull? When do you add the energy? When do you swing your legs and when do you pull on the chain? At what point in the ride?
The back.
Right there at the back, right? You're coming back, right? And you start turning around, and that's when you add the energy. Think of pushing a kid on the swings, right? When are you pushing the kid on the swings? Push them, right? They swing out, they come back, and just as they're turning around, you're adding the energy, right? You don't like push and then run over here and push again. Right? Okay? I want you to try this experiment. Don't harm children. Get on the swing by yourself, okay? Get on the swing and start swinging, okay? Get up to a nice amplitude. Doesn't have to be real high, okay? And then try to pump at random times, right? Try to not just pump at the right time, but try to pump at sort of various times in your motion. You'll notice that your amplitude will die, right? Instead of going higher, you'll just kind of... Little kids are so fun to watch when they're trying to learn how to get on the swings, right? Because they get on the swing, they sit on the swing, and what do? Right? They just kind of go for it. They know that they have to swing their legs, and they know that they have to pull, but they can't, like, there's a timing to it, isn't there? And the timing changes depending on how fast the system is going. So it takes a little bit of practice, but eventually they'll get it, right? If you don't put it in at the right time, then you don't get the high. Now, I went online and I looked for pictures of, kids on swings and things like that. And the internet, being the internet, had some great pictures. It was really hard to find a stock photo that didn't have a happy kid in it.
Oh my gosh.
Right? But, or a white kid for that matter. Sorry, trying to be diverse here. But I did find one without a kid in it finally.
Oh my god.
So, the white dog.
Hey, there's brown on it.
It's brown on, okay, good.
There's
We're
brown
getting
on
some,
it,
we're
there's
getting
fair.
some cultural diversity going, right? Okay? But as you can tell, that is a happy dog. Alright,
Oh
so
my gosh.
swings are a great example of a forced oscillation, and there's a specific phenomenon that occurs when you force a harmonic system at exactly the right frequency. Just like in the swings where you can add that energy at any point, if you do it wrong, the amplitude dies out. But if you do it just right, if you add that energy at just the right time, okay, doesn't matter how much energy you input, over time, the amplitude of that system is going to get bigger and bigger and bigger. The phenomenon of increased amplitude, when a harmonic system is driven at the frequency it wants to be driven at, is called resonance. Resonance is responsible for a lot of different things. And in your book, I'm going to get this wrong. Yeah. Resonance I'm going to do it my way. I think your book does it with frequency F instead of angular frequency omega. So there's a 2 pi difference, okay, in our equations here. But basically, the frequency for a simple harmonic oscillator, one that doesn't have friction in it, the resonant frequency is that magical omega that unlocked our toolbox, the square root of k over m. If you take a system and add energy, add a force at that frequency, then the amplitude will increase. Now, theoretically, the amplitude will increase infinitely. But we know for many oscillating systems, you can't have infinite amplitude before you either break the spring, or in the case of the swings, it's impossible to go over the top. My daughter has tried on numerous occasions, but there's just a point there, right? Where you can't swing fast enough, and the tension comes out of the system. Yeah, have you seen kids do that? You probably done this, right? Okay. Where you swing so high that the chains go slack,
Yeah.
right? And then you come back and, right? Okay, as the chains catch again. That's the point where it's no longer an oscillator, right? It's turned into free fall for a moment, right? It's coming up and then coming back down, catching up, and coming back down, catching up, right? So you've hit the limit there because there's friction and other things in that system. But in the case of resonance, right, for an ideal oscillator, it can drive that amplitude to infinite heights. This resonant frequency is responsible more than just for amplitude increases. It's responsible for a lot of mechanical failures in systems. For those of you who are engineers and going on in engineering fields, you're going to be learning about failure analysis and failure modes and all different kinds of things. And one of the things that needs to be designed out of many systems is this resonance phenomenon. For example, buildings and bridges. When are they exposed to driving forces that are harmonic in nature? Wind? Earthquakes? Basically nature, right? Wind. Why would wind cause resonance? Anybody who's ever played a musical instrument knows that resonance, or the plucking of a string, or the blowing across a reed or into a mouthpiece, sets up a vibration, and then that vibration is matched by the instrument, and then the sound is produced. That's a resonance phenomenon. Same thing can happen with buildings. Have you ever taken a blade of grass and kind of put it between your thumbs and blown across it to make it buzz? Okay? That's resonance. So that can happen to bridges and buildings. Earthquakes, right? You don't want to design a building that has the same frequency as earthquake waves. Because if you did, what's going to happen to the building? Even faster and more destructively than so Tokyo, Japan is basically a nation that built itself on an earthquake. They designed the foundations of the skyscrapers, okay, to be, they're actually floating. Okay, the foundations are not connected to the ground. There's these big suspension systems that hold up these buildings that when the earthquakes happen, the building just doesn't have the same frequency as the ground is shaking, and it helps to absorb a lot of the energy. I do want to show you one thing though, okay? That while it's a pretty bad oversimplification to say that what I'm about to show you was the fault of resonance, it's still a good movie and you gotta see it. So, my apologies to all the people in the universe that think that this is not a resonance phenomenon. They're half right.
Perhaps, among other things, the Tacoma Narrows Bridge was the most spectacular Aeolian harp in history. Unfortunately, its first performance was destined to run only about 4 months. In the meantime, she was a beautiful bridge. Beautiful, but a little strange. Even before construction was completed, people observed its peculiar behavior. That was because, even in a light breeze, ripples ran along the bridge. After a while, one of the local humorists called her Galloping Gerda. And for fairly obvious reasons, the name stuck, at least until the 7th of November, 1940. Then as now, Seattle and Tacoma were sports-minded cities. For 4 months, a regional sport was to drive across the bridge on a windy day. While some claimed it was like riding a roller coaster, Others found it a little disconcerting to see the car in front disappear. How popular this bridge sport was, or to what extent it might have spread across the country, is anybody's guess. On November 7, 1940, the winds were relatively moderate, about 40 miles per hour. A new mode appeared. Rather than rebel, the bridge began to twist. A wind of 40 miles per hour is not too strong, but it was strong enough to start the bridge twisting violently. And at 11 a.m., it fell. Investigators were mystified. A bridge constructed according to the best engineering standards of the day, perhaps the best bridge in the world. This was not a bridge that was supposed to collapse. What in the world?
That was not CGI. So, did you catch the wind speed?
40 miles per hour.
40 miles per hour. Comaneros in Washington routinely sees hurricane-force winds going through the narrow gap between the islands. 75, 80, 85, 100 miles an hour is not uncommon. And they knew that. They designed the bridge to be able to withstand wind speeds in excess of 100 miles an hour. What they didn't plan on, though, was a resonance phenomenon caused by something called vortex shedding. As air rushes across a surface and encounters the end of the surface, it'll peel off. And as the air peels off, it rotates. And that rotating air, like an eddy, okay, or a turbulence kind of thing, will impart a force perpendicular to the direction that the eddy is moving. And what was going on, they think, with the Tacoma Narrows Bridge is vortex shedding was happening on the top and bottom surfaces of the flat bridge. And at 40 miles an hour, the frequency at which the vortexes left the ends perfectly matched the resonant frequency of the torsional mode of the bridge. The bridge was twisting along its center axis. Okay, so what was happening is an eddy would peel off and force one end down, and then the next eddy would come off and force it up. And though that forcing motion was happening at exactly the resonant frequency for the torsional mode of the bridge, the amplitude built up until critical failure happened, right? So that's reinforced steel and concrete going through an amplitude of 20 feet. The ends of the bridge were going up and down 40 feet, right, from top to bottom. Absolutely incredible. Ever since the Tacoma Narrows Bridge disaster, all bridges and skyscrapers skyscrapers came later, but bridges, one of the final testing parameters that was required internationally was to put the bridge in a wind tunnel. Nobody thought to put a bridge in a wind tunnel before the Tacoma Narrows Bridge disaster. After Tacoma Narrows, every bridge, wind tunnel testing, scale model diagram, of things, to see if it could withstand any wind speed, not just the maximum ones. All right, so the whole discussion of harmonic motion has been leading up to waves and wave motion. And this is where we're going to spend, I can say it now, the rest of our semester, studying waves. We're going to hopefully cover most of wave theory today, and that will leave us with sound, right, to round out the semester. So where we're going with this, starting on Wednesday and into next week, is being able to describe hearing and to describe musical instruments and all sorts of things. But we'll get there, okay? So what I brought with me right now is something that hopefully all of you will at least appreciate and understand. It's a simulation from the internet, so therefore it's real, right? I need to be able to slow down a wave as it's going to be able to talk about what's going on here. And this can be very difficult to do, but I do want to demonstrate to you kind of, what a wave might look like. We're going to talk about different kinds of waves and things like that. So I need a volunteer. I'm going to ask Hunter. Promise I did not touch the end of that screen. Washing hands anyway. All right, stand up, Hunter. Okay, hold this up. Okay, so everybody can see it. So this is an incredible slinky. Nobody has a slinky like this. Right? Good slinky. Okay. What I'm going to do is I'm going to put a disturbance in the slinky. Okay. It's going to travel down the slinky. It's going to bounce back and forth. Technically, that is not a wave. Okay. Because a wave has to be a train of these loops, right? These disturbances that are going along the spring. So, but I needed to show you the difference between two different kinds of waves that can exist. There is a transverse wave, which is what I got pictured on the screen. And a transverse wave means that the pulse or the disturbance is traveling perpendicular to the direction it's traveling along the medium. Okay? This pulse I had pulled down, right? Okay, I can put a pulse on it by giving it a little flip too. Okay? But as you can see, the pulse, the direction of motion, of oscillation is up and down, but the direction of travel is to the side. Now what I want to do is I want to do one called a longitudinal wave. I'm going to grab the slinky, I'm going to compress it, and then I'm going to let go. Okay? And here, even though I wasn't too perfect, the disturbance is parallel to the direction of travel. So transverse, where I've got disturbance going up and down, but the direction of travel is to the side. And then longitudinal, where I have the compression, the disturbance, okay, acting along the direction of travel. So those are two different kinds. All right, put it on the ground, let go. So, just wanted to show you that with my incredible slinky. I can't show you a longitudinal wave on the screen. They're very difficult to simulate and really understand what's going on. We're going to get to them. I'll have some pictures for you when we get to sound waves. But just know that a longitudinal wave can happen in any type of medium. Okay? Solid, liquid, or gas. Transverse waves, though, transverse waves need to happen, they don't happen in liquids or gases as far as we're concerned. There's a special kind of wave called a surface wave, because what's the one example everybody thinks of when we're talking about waves?
Yes.
Ocean's always second or third in Fresno, right? It's usually light or sound or something like that. I grew up near the beach, so ocean, right? Okay. Ocean waves, water waves. That's a special kind of transverse wave. It's called a surface wave. It's the boundary between two different media types, liquid and air and gas. So we're not going to worry about that one. But for us, longitudinal waves can happen in any medium, solid, liquid, or gas. But transverse waves can only happen in solids. Defining what a wave is can be a little bit difficult. Okay? Again, we can come up with lots of different examples of what a wave is. But actually, what is a wave? Because the wave really is the pattern of linked harmonic oscillators. Nobody likes that definition, though, because it's not very romantic, right? But I want you to take a look at, okay, that green dot right there. Just look at it. What is it doing?
Not moving sideways.
It's not moving sideways. It's moving up and down, just like something you've seen before. What is that? It's a harmonic oscillator. Okay? So a wave is a collection of simple harmonic oscillators. Look at the red dot right next to the green dot. What is it doing?
Stretching and going up.
It's also going up and down, but it's going up and down with the same amplitude. It's going up and down with the same frequency and the same period. All of those things are the same for all of those dots, but they're all doing it at slightly different times. this green dot and this green dot are exactly opposite each other, aren't they? When one of them's at a top amplitude, the next one's at a bottom amplitude. And so a wave is a complicated, interconnected system of simple harmonic oscillators. And I know that sounds kind of bad, right? Like, oh, it's going to be terrible. And you're right, but we're going to hide most of that from you by lying. So, yeah, liar, liar, pants on fire. I know. So, to keep it simple, let's talk about common features of a wave that will allow us to avoid a lot of the messy time stuff that's going on inside there and focus on what's really important. Yeah. Right, so the question is, how do I define the amplitude, or where's the amplitude defined? We're going to stick with our definitions that we have from simple harmonic motion, where amplitude is measured from the equilibrium up to the highest point. Now, there's another place where there's an amplitude, right there. So just like in simple harmonic motion, right, we have our amplitudes at the same places. Now, we also had frequency. Remember frequency? What was frequency?
How quickly?
Not how quickly. How
many?
Yeah, how many oscillations happened in 1 second? Questions? Okay, and yeah, good. And then period, how long it takes, right? So all of those definitions still apply because we have harmonic oscillators in there, and they all have the same frequency, they all have the same period. But we've got to be able to handle this sort of time difference, right? This things happening at different times and in different places. We'll get there, don't worry. Okay? So we have our amplitudes, but we're going to define a new idea, a way of talking about what's going on here. And this new idea is going to be the distance between any two points on the wave that are identical. In other words, the simple harmonic oscillators at that point are doing exactly the same thing at exactly the same time. Okay? So one way to think about that in simple terms is that I can take a look at the two peaks on this wave. Peaks being a word that says the highest point, right, on the wave. The peak to peak distance we are going to call the wavelength. And wavelength, we're going to use the symbol, the Greek letter lambda. Now, what's a lambda? That's how we would spell lambda in today's language. But the letter itself, the way you do this one is, we're coming into Christmas, right? Candy canes, right? Okay. So draw a candy cane that's falling over, okay? And then it sticks its leg out to catch itself. That's the Greek letter lambda, okay? It tends to, like in typeface, it tends to sort of have a more, I don't know, curly-ish kind of thing, but don't worry about getting it the way books do, right? Just draw a sideways candy cane and then put a leg on it so it doesn't fall over. That's the symbol that we're going to use for wavelength. It's a distance. So what are the units of wavelength going to be in SI units? It's going to be in meters. All right. Now, I can do that from peak to peak, but are there any other 2 points I could measure that distance?
Trough to trough.
Okay, what word did you just use?
Trough.
Trough. I am not responsible for the English spelling of this word.
Yep.
Now I ask you, okay, English is dumb. Okay?
Yeah.
English is a language where there's rules and then you break all of them. Because how should this be pronounced? Trow. Right? Okay? As a matter of fact, I think the word trough meaning the dip, right? The bottommost point here, okay? I think you shouldn't do it that way. You should do it this way. Right? Okay? Because that's what it sounds, right? Okay. So, anyway.
Exactly.
Trough to trough distance. Yeah, you ESL students know exactly what I'm talking about. Your language is messed up. You're right, it is. The trough to trough distance, okay, it's going to be exactly the same. As a matter of fact, I could take this point right here, the equilibrium. Skip this point. Why am I skipping this equilibrium point? It's not doing the same thing. This equilibrium point's on its way up, right? Whereas this equilibrium point's on its way down. I got to pick 2 points that are doing exactly the same thing at the same time, right? So I got to skip this one and get back to this one. And if I did that distance, I would still have a wavelength. Half a wavelength. If I was measuring half a wavelength from a peak, where would I end up? I would start at a peak, and half of a wavelength would bring me to a trough, wouldn't it? So wavelength becomes a handy way to kind of talk about kind of where we are in relationship to other portions of the wave. Okay, so the question is essentially, what is the relationship between wavelength and everything else, like the amplitude and the frequency and the period? Okay, what happens if I change the wavelength? Okay, now I want you to know I'll paid Jorge to answer that question, perfectly timed. Okay, because of what I want to show you right now. Okay, which gets back to this simulation, right? Because I froze it in time. But now we need to talk about what happens as time passes. And this is going to be a frustration you're going to have when you're dealing with waves. Because your piece of paper is not animated. And when you draw a wave, really what you've drawn is a snapshot of it in time. But it evolves. It moves. This wave is moving to the right. So can we define, I promise I'm going to answer your question, right? Can we define a velocity? The velocity of what? Yeah. You see it moving across there? We can track this peak. Can we track this trough? Can we track this equilibrium point? We can pick any point on the wave and measure its velocity. How fast is the wave traveling? Frequency. Frequency is how many times an oscillator goes up and down in 1 second. But in the case of a wave, the exact same idea is how many peaks pass a certain point in a certain amount of time. I'm going to go and I'm going to adjust the frequency of this wave. Okay? I'm going to take the frequency and I'm going to increase it. Watch what happens. The number of dots that pass my laser pointer, has it gone up or gone down? Up. There's more dots, right? Takes less time. The period went down, but the frequency went up. Frequency increased, period decreased. That's exactly what happens in an oscillating system, right? They're inverses of each other. But now I've got more of these. Let's see if it's probably a little, I'll ramp it way up, okay? So here's the frequency. It's like about 1 second, right? Okay? And then if I bring it way down, too far. Right? If I just sort of grab that point right there, do you see how much time is going by before I get to the next peak coming by? Right? So frequency would be like standing next to the wave, okay, and watching peaks go by. Frequency is the number of peaks per second, or number of troughs per second, a number of equilibrium. Pick any point on the wave, make sure it's the same point every time, right? And you've got your frequency. So what happened to the wavelength as the frequency increased? It got shorter. In order to have more peaks per second, those peaks have to be closer together. As the frequency decreases, the wavelength gets bigger. But what do you notice about the speed of the wave? Is this one moving faster or slower than the one we had before? Now, grant you, the individual oscillators are moving up and down faster. But look at the speed of one of these peaks. It's going about that fast across the screen. So lower the frequency. How fast is it going? It's the same speed. I know it feels slower to you, okay? Because look, obviously it's doing it slower. The speed is exactly the same, okay? So let me disabuse you of a certain idea right now, okay? Somebody's phone where? Or is that out in the hallway? We can hear your music! Okay. Chemistry professors. So let's link a whole bunch of things together. You're going to see an equation that relates the speed that a wave is traveling to its wavelength and to its frequency. First of all, wavelength units of what? Frequency units of what? Hertz, which is a what? 1 over a second. So you take a meter and multiply by a 1 over a second. What do you get? Meter per second. So unit-wise, this works out. But, and let me be clear, this equation is not the relationship between velocity and wavelength. It is also not the relationship between velocity and frequency. This equation is a trap. It's the relationship between wavelength and frequency. The speed of a wave, I'm going to say this a lot. The speed of a wave depends on only one thing. The properties of the medium in which it is traveling. The speed of a wave is set by the material that the wave is moving through. So the speed of a wave in air depends on what? Air. The properties of the air, its density, its temperature, its pressure. The speed of a wave in water depends on what? The water. Speed of a wave in steel, the speed of a wave in helium, the speed of a... all of those waves have different speeds because the material or the medium in which the wave is traveling is different. But what happens if we don't change the medium, we keep the medium the same? What happens if we increase the wavelength? If the wavelength goes up, in your mind, what does that look like to a wave? The wavelength is getting bigger. What's happening to the wave? It's stretching out. The distance between peaks is getting bigger and bigger. Mathematically, if lambda gets bigger and v has to stay the same, then what happens to the frequency? It has to get smaller. As those peaks stretch out, fewer and fewer of them can pass by the same point in space in the same amount of time. What happens if the wavelength goes down? Does the velocity change? No. Because the velocity of the wave depends on the material. The medium is the word we use in physics. Okay? The medium of the wave. All waves require a medium. No medium, no wave. Why in space can nobody hear you scream? There's no air for the sound wave in which to travel. Okay? So, be careful with this equation. Like I said, it's useful. We use it a lot. And sometimes you think that the speed of a wave depends on its frequency. It does not. Can you find the speed if you know the frequency and wavelength? Yeah. Sure. Right? But when it comes to changing things, wavelength and frequency will change as long as the medium doesn't change. Everything else that we know from simple harmonic motion kind of comes over. Okay? Not the entire toolbox, okay, but the more useful bits. Now, we do have to talk, though, about how to mathematically describe a wave. And conveniently, waves look a whole lot like sine and cosine. So it shouldn't come as any surprise that we use sine and cosine to describe them. I believe your book standardizes on cosine, which is fine. Okay. Again, it's starting conditions, all that sort of jazz. Okay. But I want to point out something to you. This right here is called a wave function. It's a mathematical description of a wave. Now, as you can see, it's got amplitude in it. It's got cosine in it, which is good because we need the wiggle. But then it's got a k and an omega as constants, and an x and a t. You will not actually see this one in your book. Your book will actually write this one slightly different. Okay? The way your book will write this is a way that I actually don't really see anywhere else. Okay? Is 2 pi x over lambda minus make sure I get this right. Yep. Omega is equal to 2 pi ft. There we go. Okay? That's how your book will write it. They'll use lambda and f. The rest of the world uses k and omega. So what is k in this case? It's not the spring constant. On behalf of all physicists everywhere, I wish to apologize. But there are 26 letters in the alphabet, and we have to recycle at some point. Okay? So, K is not the spring constant. Which is bad, because this is so closely related to simple harmonic motion that could be confusing. I give you that. Okay? But in the context of a wave and a wave function, K is called the wave number. And it's defined as 2 pi divided by the wavelength. I think it boils down to the fact that physicists in particular and engineers by extension really don't like fractions in their formulas. So we'll do anything in our power to simplify and reduce our equations down to nice flat things. Okay? So just be aware of that. In the context of waves, whenever you see a k, it's going to be the wave number. 2 pi divided by the wavelength.
My book says the sine function with that.
Yeah, you can use sine or cosine,
Sine
doesn't
and
matter.
cosine? Oh, okay.
Yeah, as a matter of fact, Yeah, you got the older edition. I think they switched to cosine in the newer edition,
Oh,
right?
really?
Okay. The sine or cosine doesn't matter because I can add a plus phi in there, that phase angle, and add 90 degrees and get right. So it kind of just really depends on whether or not your wave starts at 0 at time 0. It doesn't actually matter all that much because in theory a wave should be infinite in either direction. Okay? It's coming from infinity far away, it's going to infinity. We're not going to terminate our wave yet. Okay?
But the kx minus the omega t, we could call that a constant still.
No, this is definitely not
Okay,
constant.
because it says in the book it equals a constant. I don't know why it says that.
If the time stays the same,
Oh, okay.
right?
That's why.
What the heck is going on down here? When we had simple harmonic oscillators, all we had was sine or cosine omega t, didn't we? Okay? That's because in time, the oscillator really just more or less stayed in one place. It was going up and down in one dimension. Okay? But time gave us that one dimension. But look at how I've written this function. It's a function of position and time. This isn't your first space-time equation. Drop that one on your date on Friday night. Okay? But this is really the first time that we've had to deal with both of them simultaneously. Okay? What do I mean by that? That function right there is the animation I showed you. It's how this wave is evolving in space and time. Notice it uses y. What is y? What is y? You know what y is? It's vertical displacement, right? X, horizontal. And when I go and I draw this wave, I better use cosine. Okay? Like that. I have not drawn the time version. Because what happens to this wave in time? The peak that's at the 0 on the x-axis is going to go where? It's going to go to the right. Okay? So I can't draw the time. I can draw frames, right? It's like frames of a movie or frames of an animation. I can draw it there, and then I could draw it when it's kind of over here, right, where it's shifted a little bit, and I can continue to draw it. But without an animation, I can't draw what an actual wave is happening. So when I draw a picture like this one down in the corner, basically what I've done is I've frozen time. So what this function does is it gives me what the vertical position is on my wave for any horizontal position at any time I happen to choose. But more importantly, it gives me a way of quickly summarizing and figuring out what the mathematical description of a wave is. And what do I mean by that? Let me do two examples that shows you the power of the toolbox of waves. Okay? So in this example, this is something I expect you to be able to do. Okay? Given information about the wave, can we write down its mathematical description? Right? So what do we know? We know amplitude, we know period, and we know wavelength. We want to find a function that mathematically describes this wave. Now, on the surface, that can sound pretty horrible, right? Like, oh my gosh, that function is so complicated, and you got to go out and take lots of pictures of the wave. The toolbox, again, I'm hiding a lot of stuff here. The toolbox is so universally applied that we can basically go, look, we know that the mathematical format of any wave has to look something like this. We just need to be able to find the k and the omega, the wavelength and the frequency. If we know those things, then we know what the function looks like. So, how are we going to find our k? Well, we're going to find the wavelength divided into 2 pi. How are we going to find omega? Well, we're going to find the frequency. We're going to multiply by 2 pi. So, have they given us any information that we can use to find these two things?
They gave us the wavelength.
Gave us the wavelength, okay? 2 pi divided by a wavelength of 2.5, which I don't know. 2.5 is 5 halves. So this is 4 pi over 5. And then my frequency. They didn't give how do I find my frequency? Oh, I got the period. Period is the inverse of frequency, right? Okay. They said that it's 3 halves, so this is 2/3. So if I come over here, my omega is going to be 2 pi times 2/3, which is going to be 4 pi over 3. And so now I can go ahead and write down this function. I needed amplitude, I needed wavelength, I needed frequency. If I know those things, then I can mathematically tell you what my wave is doing at any time in any place. It's going to be 0.6. Why 0.6? That's its amplitude, okay? Times my k value, 4 pi over 5x. X and t are the variables, right? Minus 4 pi over 3t. So there it is. There's the function that describes my wave. If I want to know what my wave is doing 6 seconds into its lifetime, can I do that? What do I put in for t? 6 seconds. If I want to know where the wave is, right, at 2 meters over, I put 2 meters in for x. What mode must your calculator be in? Radians, because the units inside there are unitless. So, keep that in mind. Now, one thing I didn't mention, back when I did the other slide, let's see if I can pull that one up. Where's my toolbox slide? No. This one. Okay. This one is for a wave traveling to the right. If the wave is traveling to the left, there is one very tiny change. Okay? That very tiny change, did you notice it? There's a plus sign in it. Again, actually, no, I'm not going to apologize for this one. This one's math's fault. You go take it out on your math teacher for this one. Okay? But if you tell a program to animate this function, right? Put in a bunch of values for x and t, and let time run. Okay? If you run time in the forward direction, then you need a minus sign in that function in order for the peaks to move in what we call the positive x direction. It's just kind of how trig functions work. Okay? Same thing goes for the plus sign. The plus sign will actually move these things in the negative x direction. So it's a little bit backwards, right? I know you want to see that minus sign and think, oh, that's left. No. Okay? It has everything to do with the evolution of trig functions. And like I said, I'm not going to apologize for math. Math is dumb. All right. Mathematicians are awesome, but math is out to get me.
Math is dumb, English is dumb. What is it dumb?
Physics is not dumb. Physics brings it all together. Okay. You can do it in reverse. If we know the function, right? If we can take a picture of a wave and measure, right? Frequency, all that kind of stuff, write it out, then we can do it in reverse, right? So just reading right off of this function, can you tell me what its wavelength is? Well, yes. But let's be careful. This one was written kind of nicely. We know that k is equal to 2 pi over 3, right? But that also has to be equal to 2 pi over lambda. When I solve that for lambda, I get the wavelength. The pi over 6, what is that? That's omega. Okay? And omega is equal to 2 pi f. So what is f going to be equal to? Right? I can just read right off of that function what these values are. What is the amplitude? They didn't ask me for it, but I can tell you what it is. It's 10 meters. Okay? How are we going to find the speed of this wave? We can do lambda times f. Okay? So let's see. Lambda is 3. Frequency is 112. So that's 1/4 meters per second. By the way, instead of using lambda and f, we can use k and omega. Right? So instead of lambda, we're going to put in right? And instead of frequency, we put in that. So 2 pi over k times, I did something wrong. Yep, this one I did wrong. Right down here. 2 pi over, no, come on, Mr. Balo. Today's class is brought to you by Dayquil.
Oh my gosh.
Omega over 2 pi. That's what I wanted to do. Okay? And so this is going to be omega over 2 pi. Two guys cancel. So another way to do this is to do omega over k. Right? So just have that in your toolbox so that you don't have to do that. Can you tell me which way this wave is traveling? To the right or to the left? How do you know?
Plus signs.
Plus. Right? And here, now I've taught you the foreign language of waves. Right? Any wave, done. I don't want you to confuse these wave functions with something else called the wave equation. The good news for you is that you are not going to be required to work this function out in any of its horribleness. Okay? But I want to show it to you for two reasons. First of all, you are going to encounter it. Yeah, exactly.
Oh, partial derivative.
Okay? Right? And you're going to encounter it, and it's going to be confusing. You're going to think, oh, this is a wave function. It is not. The wave equation and a wave function are different things. The function is the y of x and t we put into the wave equation. The wave equation is the master equation that tells us our functions actually act as waves. I know this is a little bit confusing, okay? And it's doubly confusing because what you are staring at is a second order partial differential equation, okay? Which many of you have not encountered yet. You probably haven't encountered partial derivatives, let alone differential equations, okay? The short version is this. Partial derivatives is what the universe does. All of those derivatives that you've been learning in your class, worthless. Okay? Because the universe tends to treat variables as independent entities. There are some that are connected, but most of them are independent of each other. And a partial derivative fixes that. You know all that horrible chain rule stuff you had to learn in 5A?
Yeah.
Okay? Gone. Partial derivative with respect to x, anything that's not an x is a constant. So what's the derivative of y to the natural log of x with respect to x if it's a partial derivative? Don't think about it. It's 0. Because y is a constant value. Okay? Oh, I put an x in there. Never mind. Natural log of 3. Alright. Okay? Again, this lecture is brought to you by Dayquil. It's really hard to concentrate when you're on cough medicine. So, when you have a partial derivative, anything that isn't specified is treated as a constant. Over on that side, it's time. Over on the other side, it's position. Right? So what happens is we use this to show that that wave function I showed you actually works. When you take its second order derivative, what's the second derivative of a cosine function? Sine. And you do that on the spatial side with just the kx, right? Because omega t is a constant, 0 in that thing, right? And you do exactly the same thing with the same function on the other side. What you'll end up with is a relationship for what v is, and v turns out to be lambda times frequency or omega over time. Okay? So what this does is it proves that our wave functions actually work, and vice versa. Any function that satisfies this master equation is the equation for a wave, is the function for a wave. Again, there's two reasons I'm showing this to you. I don't want you to confuse this with the function. This is the master theoretical equation that you don't have to worry about yet. You will have to worry about it in Physics 4C, which is the second reason I'm showing you this. Because in 4C I want to go and say things like, do you remember in 4A when I showed you the wave equation? You go, no. I can say I did. I did. It's on YouTube now. So, there you go. It'll come back. It'll come back. We're going to talk a lot about waves in Physics 4C. All right, a couple more things, and I will actually be right on time. What does the speed of a wave depend on? Medium, the material which it travels. So if we're going to talk specifically about strings, which we're going to do for a while, so this would be a wave on a slinky, a wave on a guitar string, a wave on a violin string, anything like that. The speed of that wave is going to depend on the properties of the medium. And so specifically for strings, tension in that string, anybody that plays guitar or plays a stringed instrument knows, as you change the tension by turning one of the tuning pegs, what happens to the frequency? Goes up or down, depending, tension increases, frequency goes up. Well, why does the frequency change? Tension change, which changed the speed, because the properties of the medium changed, right? And everything else changes along with it. Now, there's another symbol in there that is not the coefficient of friction.
Oh.
It is mu, the Greek letter mu,
Okay,
but
so-
here, mu is the mass per unit length of the string. Basically, how much material does the string have in its length? On a guitar, the thick strings produce low notes. They have a high mass per unit length, okay? Which correspondingly makes their velocity slower. Right? Big number in the denominator of that, okay? Whereas the high-pitched strings are the thin ones. Very little material for their length. So, just pointing out, clarifying things for you here, okay? And then, to round things off today, reflection and transmission of waves. This is the rule. When a wave bounces off of a material that is not free to move, it inverts. A peak going into a wall, say a wave running into a wall, will come off of that wall as a trough. However, if the medium is free to wiggle, say the end of a rope, okay, and the end of that rope can flap around, then as it gets to the end of the rope and comes backwards and bounces off, bounce being a very strong term here, it will maintain its orientation. A peak will stay a peak. Waves reflect all the time. A sound wave on reflection is called an echo. You don't hear echoes normally every day. You need to have sort of long distances in order for the sound to travel and get back to you to hear that echo, that response, right? But the sound waves that are bouncing off the walls of this room are going in one way, their orientation, and then they're coming off upside down. Okay? What physicists call inverted in their phase. I've run out of time to show you the videos, so make sure you look in the book. Okay? There'll be pictures. You'll see a picture where a string is tied to a wall. It'll come back upside down. You'll see another picture where the string is like free to wiggle up and down on a pole, like with a ring on it, okay? That one will come back having maintained its orientation. We're going to use that idea on Wednesday to talk about a very special kind of wave called a standing wave, which will then lead us, after Wednesday, into the science of sound. And I will see you on Wednesday, whether